Okay, so here we have lesson 1B, which is the second part of the first lesson. Again, another very short lesson, but this is about electromagnetic waves and what these are all about, because they're very different than sound waves. So we've looked at mechanical waves. Those are sound waves. Another type of waves, that we kind of use to intro, this kind of wave motion, periodic motion, etc., etc. But now we're going to look at this crucial kind of wave, the electromagnetic wave. Okay, and it's really, really important. Basically, light is a wave of oscillating electric and magnetic fields. So you can see the electric field, which is, I guess, in the y direction in this case, up and down. And that's an oscillating electric field. And then the magnetic field, I guess, would be in this kind of like x or z direction, whatever you want here. And then the speed of the wave propagation, is perpendicular to both of those, and so the wave is really in 3 space. Now, this is really, really, really hard to envision. If you're like most high school students, it is really hard to wrap your head around what an oscillating electric field looks like. And then an oscillating magnetic field is even harder to imagine. And last but not least, those two things oscillating perfectly in sync and then traveling in a third direction is even more difficult to imagine what that looks like. And if it's not difficult for you to imagine what it looks like, either you're a genius or you're not really appreciating how complex this is. And I would say it's probably the latter. Anyways, we're going to look at electromagnetic waves, and we have 5 properties that they all follow, okay? And these are properties of electromagnetic waves, and this is kind of what informed some of the research on these things. So electromagnetic waves are made up of alternating, oscillating electric and magnetic fields, okay? So they flip from being positive to negative to positive to negative to positive to negative, north to south to north to south. They're oscillating, which means they're harmonic in their terms. They go back and forth, and they're made of electric and magnetic fields. Okay, the electric and magnetic fields are perpendicular to each other, and you saw that in that diagram. The electric field was in y, the magnetic field was in x. Okay, so they're perpendicular. The vibration of the electric and magnetic fields is perpendicular to the wave's motion. So electric and magnetic fields are perpendicular to each other, which are also mutually perpendicular to the direction of the wave. Electromagnetic waves are transverse. The electric and magnetic fields vary sinusoidally, so they're sine functions. That's what this means. And they're in phase with each other. So when the magnetic field goes to 0, the electric field goes to 0. When the magnetic field's at a maximum, the electric field's at a maximum. They maintain the same phase continually. Okay, that's important. Always in phase. Electromagnetic waves travel at the speed of light. Okay, that's why it's called the speed of light. But this is what electromagnetic waves travel at in a vacuum. In other mediums, they travel at different speeds, which causes refraction, and we're going to talk about that in part C of this lesson. So the speed of light, we can talk about now. Recall from grade 11 physics, universal wave equation, V is equal to F lambda. V is the speed of the wave, F is the frequency, lambda is the wavelength, okay? So here we kind of learned that James Clerk Maxwell, he was the one that proved that light was a traveling wave of electric and magnetic fields over time. Many different types of electromagnetic waves have been added to the list. So we use the electromagnetic spectrum to kind of indicate, oh, all of these things are the same, they just have different energies associated with them. So here's the electromagnetic spectrum. So the radio waves that your car would pick up at its antenna, electromagnetic waves. The microwaves that we use in our microwave ovens to heat food and drinks. Infrared radiation, visible light, ultraviolet radiation, X-rays, gamma rays. All of these are electromagnetic waves. So they're all the same thing. They just happen to have different frequencies and different wavelengths. Okay? There's Maxwell right there, king of the beards. Maxwell also proved that electromagnetic waves travel through vacuum at the speed of light, which is very, very convenient. There's kind of a little derivation using some of these constants that we've used. This is an electric constant. This is a magnetic constant. Some of these you may have seen before. But if you take this relationship 1 divided by the square root of epsilon naught times mu naught, you will get 3 times 10 to the 8th. This is not that important for our course, but it kind of shows you where it comes from. All right. Let's work a little bit with the speed of light. Calculate the time it would take us for light to reach us from the sun. The sun is 1.49 times 10 to the 11 meters away. Compare this value to the time it would take a supersonic plane to fly the same distance at Mach 3. Because Mach 3 is pretty fast. Let's take a look. So here's the distance. Here's the speed of light. Here's the speed of sound. Mach 3 is, of course, 3 times the speed of sound, which is 996 meters per second. We can already see what's going to happen. Distance equals velocity of times time, because light does not accelerate, so it's safe to use this formula. We'll rearrange. The time that it would take for light to travel from the surface of the sun to the surface of Earth is 497 seconds, which is not that long. Divide 500 by 60, and you don't get that many minutes. The time it would take for sound to do this is 1.58 times 10 to the 8 seconds, which, if you do a quick little conversion, is about 5 years. So if you fly at Mach 3, it's going to take you about 5 years to get to the sun. Light does it much quicker. All right. Infrared light is invisible to the human eye, except through special sensors. Given the range of wavelength of infrared light, calculate their corresponding frequencies. Now, we can always go into our textbook and look up the different ranges of infrared light. This is all information that's kind of readily available to us. And so let's work with V equals F lambda to try and find some frequencies. So here's the approximate range that we got from the textbook, and this tells us the infrared goes from a wavelength of about 1 times 10 to the minus 3 all the way up to 7 times 10 to the minus 7. Frequency is equal to the speed of light, c, divided by lambda. Okay, so you'll notice that we've stopped writing F is equal to V over lambda because we know that this is a special velocity. It's the speed of light, so it's always going to have the same value. So we get 3 times 10 to the 8th, and we divide that by 1 times 10 to the minus 3, and we get 3 times 10 to the 11th hertz. So that's for this baby down here. Now we're going to shift and we're going to do this one. Same calculation, 3 times 10 to the 8th, divided by 7 times 10 to the negative 7, and we get 4.3 times 10 to the 14th. And we'll shove that into one of these relations. The frequency is greater than or equal to 3 times 10 to the 11th, but less than or equal to 4.3 times 10 to the 14th hertz, approximately. And that is the end of lesson 1B.